Hello, today we're going to discuss waves and sound. A wave is a disturbance of energy that travels through matter or a vacuum. It is not matter that travels itself, but the energy that travels through matter or through a vacuum, depending on the type of wave. The frequency of a wave depends on the source that's creating the disturbance, be it the frequency of a sound wave, the frequency of a light wave, the frequency of a water wave. All those things depend on the source that's creating that disturbance. The speed of a wave depends on the medium through which it travels. Light obviously would travel fastest through a vacuum, then through air, and then a little bit slower in glass, and a little bit slower in water. Same thing with sound. Sound travels slowest through air, and then a little bit faster in a liquid, and a little bit faster in a solid. So those speeds of those different waves depend upon the medium that it's traveling through, not the source. First thing we're looking at is the wave-speed relationship. And so some definitions here. The length of one wave is defined as the wavelength. The time it takes for a wave to pass a given point is the period of the wave. And the frequency is the inverse of the period that we talked about before. So if we first look at this equation that we've been using all semester long, V equals D over T, kind of like what we did with circular motion, the distance of one wave is this wavelength. This is the Greek letter lambda. That is the wavelength. And we know the time it takes that wave to pass a given point is the period. So we can say that the wave speed, the speed of a wave, is equal to the wave's wavelength divided by the period. And we know 1 over the period equals the frequency. And in physics, we like to have all of our equations on one line. And that leaves us with V equals lambda times F. So wave speed equals wavelength times frequency. We have different ways of categorizing waves. Our first one is if they are longitudinal or transverse. And these categorizations depend on the direction of the vibration compared to the direction that the energy is traveling. So with our longitudinal wave here, you see that these objects are vibrating back and forth. Okay? The vibration direction is this way. And the energy of the wave is traveling from left to right. Okay, so we have a wave source here, this red thing on the end is causing the wave to move, and that's pushing that energy to the right. Oops, did not mean to do that. Okay, with the transverse wave, the direction of vibration is up and down. However, the direction of motion of the wave is still left to right. So we have different ways of categorizing waves based on this direction of vibration compared to the direction that the wave is traveling. Longitudinal waves are made up of two different types of regions, compression regions and rarefaction regions. If we look at this diagram here, a compression region would be right here, and right here, right here, okay, where there's a high density level. The rarefaction regions are these opposite looking ones that have the longer spaces between them, less dense regions. A wavelength of a longitudinal wave is the length of one compression region plus the length of one rarefaction region. So a little bit different than you're used to in terms of thinking about wavelengths, but a longitudinal wave is a little bit different than a transverse wave, which was what you're used to. Our only real example of longitudinal waves is sound. Any other kind of longitudinal wave we'd have to create with a slinky, some kind of just arbitrary created situation. But our only real situation that we see is a longitudinal wave is sound. Transverse wave is the type of wave that you're more used to. The crest is the top of the wave, the trough is the bottom peak of the wave. The amplitude is the distance from the equilibrium point to the top of the crest or the bottom of the trough. Okay? And then wavelength is the distance from crest to crest or from trough to trough. So this distance right here would be the wavelength lambda, as you can see it labeled there. Okay? So transverse wave is the type of wave you're a little more familiar with throughout your life. So hopefully you're okay with that. The other way we categorize waves is if they are mechanical waves or electromagnetic waves. We're really only going to focus on mechanical waves in this course. And mechanical waves are those waves that require a medium through which to travel. So a water wave, a sound wave, people making a wave on a string, those are all mechanical waves. Electromagnetic waves do not require a medium through which to travel, and those are light waves. So all the different types of light, radio, infrared, visible, ultraviolet, X-ray, gamma rays, all are electromagnetic waves. They can travel through a vacuum. Okay, they do not require a medium through which to travel. We're not going to spend much time on those in this class, but do know that's the other way that we can categorize waves. So we put those things together. We would describe sound as being a mechanical and longitudinal wave because it requires a medium through which to travel and it vibrates back and forth. Water waves, we'd say, are a mechanical wave because they require a medium, but they are transverse waves because it goes up and down. The direction of vibration is perpendicular to the direction of motion. And light is an electromagnetic and transverse wave. It travels through a vacuum, so it does not need a medium, and it's transverse because of the direction of the vibration compared to the direction of motion. Okay, we're going to briefly talk about sound here. Sound requires a medium through which to travel. It is a mechanical wave. So my favorite reference there is the movie Alien, which came out long before you were born. But the tagline on the Alien movie, as you can see over here to the right, is that in space, no one can hear you scream. And that is a true statement because in space there is no matter through which sound can travel, and therefore no one could hear you scream. The other thing about sound, which makes it a longitudinal wave, is the particles vibrate in the same direction that the energy travels, as you see here with this tuning fork. When you hear someone speaking, it's not like the air molecules in their throat are coming to your ear. There's a constant interaction of the air particles going from their throat to your ears to hear them, but it is not like there is those particles traveling from point A to point B. There's constant interactions in between them. All right, a little bit more about sound. The normal human range of hearing is between 20 and 20,000 hertz. The frequency of sound that we hear we call pitch. So the higher the pitch, the greater the frequency. The loudness of sound depends on the amplitude of the wave. So over here on the right, you see a low volume wave has low amplitude, and a high volume wave of the same frequency. Notice the crests are on top of each other. So it's the same frequency, same wavelength, but the amplitude is greater, so it's a louder wave. The speed of sound depends on the medium through which it travels. It's faster in more tightly packed substances, so solids, it travels very quickly. Liquids, a little bit more slowly, but still faster than air. That's why when you're underwater and somebody comes up behind you, if you're underwater, you can't tell which ear they're over, which shoulder they're over, because the time it takes for them to reach, the sound waves to reach your ears is essentially the same. And then the slowest in gases. In air, the speed of sound depends on the temperature. So the higher the temperature air, the more those air particles are interacting, and the faster that the sound waves would travel. The speed of sound in air is defined by this equation. At 0 degrees Celsius, the speed of sound is 331 meters per second. And then every degree warmer, it increases by 0.59 meters per second. So in a room temperature room, you would multiply 0.59 times the temperature in degrees Celsius, add that to 331, and that would give you the speed of sound in air. Thanks.